Hello everybody and welcome to Lean Day 7. This has been recorded on the same day as Lean Day 6, so I guess it's not really much more of a day increase. It's more of a time increase by like an hour or so. I don't know. Anyway, last time we looked at implications, which uses the arrow. Today we're going to be looking at functions, which also uses some arrows. So good thing we introduced that before. So functions are going to allow us to do a lot of new things. Before we only had propositions imply propositions. Now we can do naturals imply natural numbers, naturals imply booleans, booleans imply naturals, etc. There are a lot of things we can do, and we are going to do them. So let's get started. What if we wanted to just take, we're going to make it really simple to start. What if we wanted any natural number we put in to just give 0? To be super simple, a natural number basically implies 0. It's really just a natural number, but we're giving an explicit return type. So what we're going to do is very similar to before. We're going to make a definition. I'm going to call it 0nat. And it's going to take in some natural number. Now, if you want to do this, you can do \NAT. Apparently, you can also do \uppercase N. And what we want is a natural number. And we're going to make an explicit return type with this bind. And it's going to be 0. So we're going to put in a natural number. It's going to basically give us a natural number, but it's explicitly going to be 0. So let's go ahead and check this. Oh, I actually got the O up here. I was like, why isn't it working? Yep, so we have a natural number applies a natural number. If we try and do that with 0, well, check's not going to really do any of the work yet. Right? It just knows that the output is going to be our natural number. So when we go ahead and reduce it, I actually started putting in all of that. We're going to see that it's 0. But we can change this to anything. Let's call it 7. Still 0. It's because of our explicit return type. And if we decide to change that explicit return type to something else, we'll find out that it does work. Now you might be thinking, what if could we just return it to itself? So whatever we put in is itself. It's basically an identity. So let's do an identity nat. I can't write identity. So identity natural number. And that's going to be an input in, I want to try this again. Ooh, it does work. I've done that. I might do that now. Yeah. Okay. So we have our natural number. We're going to get a natural number. But now we need our bind. And since we've already given an input, we can use that now. Just like in functions. So if you have f of x, you're basically going to be using f of x x in that function f. So in this case, we can put an n. And when we go ahead and reduce this, let's do 5 first. We see that it gives us 5. If we try 7, it gives us 7. If we try 1234, I put in another number, we get 1234. So that's exactly what we expected. No surprise there. But the important thing is to remember that we are still using our implication rules. Right? Let's take this off real quick. Still an implication. So nothing's changed in that regard. Let me save that file. Now we're going to talk about lambda functions. Lambda functions are very helpful when you want to make just short inline functions. you're not really defining it somewhere else. You're defining it right then and there. It's going to go away immediately afterwards. And this can really help you if you want to read your code quickly. You just don't want to define it somewhere else because then everything is everywhere. You want to keep things concise. Now we're also going to show that you can abuse Lambda functions and it might make your code worse and that is less readable. So we're going to do 3 examples. We're going to define, let's go with our 0nap4, prime it to change just the name, natural number, apply the natural number, and we're going to use our land function. You can do \fun, you can do \lam, lambda, lambda. Yeah, there's a lot of ways you could write it. What's the shortest way actually? Let's see what we got. GL. That's pretty short. I'll just get the shift. So it's basically 3 buttons. I'll go with lam or \fun, whichever you're feeling. Just don't write out lambda. That's kind of silly. So we're going to have our natural number. That's going to be basically our input. It's a natural number. And we're going to use it and do our explicit bind. So that 0 is also a natural number. We're going to be outputting 0. So because our type is a natural number to a natural number, we need a natural number to a natural number, or it's just going to really hate us. And you don't want it to hate you. Let's go ahead and check that. And we can see that it works basically how we expect it to work. We can just go ahead and do deuce and see that 0. Now we're going to go ahead and do it in 2 different ways. These help you shorten it, and they use Lean's great inferences. Lean's just basically a type checker. It can infer a lot of information. So if we want to go ahead and do the same thing as before, so natural to natural, we need a bind, use our lambda in 0. Then you can just basically infer that for this lambda, n is a natural number, 0 is a natural number. That one's actually pretty obvious that 0 is a natural number. And note that it can be applied to this. And so this is actually just the same as what we had before. We could even take it a step further and just go with straight to the bind, lambda, n is a natural number, and 0. And there we go. So we've taken out the whole statement of what the type is, and we've gone straight to the bind section, basically our proof section. So what do we have here? This must be a natural number. We already know this is a natural number, so it leads pretty good inferring that the type is going to be natural to natural. This could make your code way less readable, so I would kind of stay clear of that one. But the other 2 I think would be totally fine to use. Alright, so let's start going into slightly more complicated things. Actually, we can do our lambda with identity nat as well, just before we really get into things. Identity is just a natural number to a natural number. I mean, that's pretty obvious, right? You can also actually just do nat. I might do that. a lot. Lambda n n. I forgot to put the prime on this. And that's just a different way of stating this right here. Alright, so let's do some more interesting functions. How about a double function? Just like 2 times whatever input we give it, as long as that input's a natural number. So double, here's our input, and our bind, and this is going to be 2 times n. Let's go ahead and check this. And we can see that it's a natural number to a natural number. So yes, Lean is pretty good at inferring these sorts of things. If we wanted to, we could write nat to nat, but again, it's not necessary. Let's reduce double of 3. What do we expect? 6. What do we get? Fun. We get a lot of fun because this is sort of not a natural to natural. I lied. But then what is it? Well, it's essentially going to be its own type after this. But when we go ahead and reduce it, we get 6. So it's totally fine regardless. But it is a natural number. I'm actually not sure why that worked. Let me try that again. Ah, okay. I wonder if parentheses will actually just... Nope. Let's see what we've got here. So it doesn't like that just we have this section here. I suppose we could do that. It's a natural to natural, and that we have in as our input, and we could basically go ahead and just swap it to a lambda function. So lambda is a natural 2 times n, and that would also work. Yeah, I'm disappointed that the previous one didn't work. Actually, it's probably because I did natural to natural, and it's only a natural. Let's go back to that real quick. Let's take out this natural. Hey, there we go. That's why. So yeah, there's a lot of ways you can write these. Just be careful which one you choose. I am not a professional at this, and that's why I mess up a lot. But we're all human. We're all human. So let's go ahead and try square. These should all be starting to get pretty simple now. We pretty much know what to do now. We can just skip right with the bind because it knows it can infer this. We can reduce square 2. What do we expect? 4. What do we get? 4. I believe you can also use evaluate. Yes, you can. 4 times 4 is 16. Prove me wrong. I hope you don't. And again, we could also use this with a lambda function. Let's do that right now. Pause if you want to make sure it works yourself. And that's how you would do it. Now, I believe we could also do just other numbers as well. Oop, there we go. So integer type, and that could also work for you. All right, so now we have established square, which is a-okay. But what about we use some booleans instead? So we'll take, let's say, a natural number, and we'll convert it to a boolean. And you're like, whoa, we've only been doing the same type to a type of that type. So for example, proposition to a proposition, natural to natural, but we could do a natural to a boolean. So what do we want? Let's say that, make a comment here, if n is greater than 0, then true. Remember, TT is a boolean. True, so written TRUE, is a proposition. Else, false. So how do we put this into lean? Here's what we can do. Let's make a definition is positive, because that's essentially what we're checking here, right? We'll have n is a natural number. We're going to get a boolean out of this. That's going to be our type. And how will we express this? Well, we express this simply as n is greater than 0. And it's going to check it for us, whether or not that is actually true. Let's go ahead and check this to see what kinds of types we're working with. Is positive. Did I spell that wrong? Oh, I wrote positive here. And we can see that we can convert a natural to a boolean. So natural implies a boolean. So let's have some fun with this one. I'm gonna write a lot of checks here. Let's put 1 in. We know that is positive 1 is a boolean. How about we reduce that? We can see that it's true. If we have something crazy, it's gonna hate us. Because remember, we're working with natural numbers. What if it's 0? Well, that's false, because we don't really know if 0 is positive or negative. It's kind of in a limbo state, right? So that's how we could basically make a bit of an if statement, right? And of course, you could do this with a lambda function. You can try that on your own if you're curious about that. But let's move on. So how about we actually just explicitly state if else? All right. So what about a function that returns boolean true if a given natural number n is greater than or equal to 0 and less than to some arbitrary number? I guess we'll do that later. And we're going to do this in lambda notation first, and maybe we can put it into ordinary notation. All right, so let's get on with it. So call it uint32. What do we have? We have a natural to a boolean. That's our type. Our bind. let's have our lambda function taking in that beautiful n. And here's how to do if else. So we can have an if n is greater than or equal to 0. And we already talked about and, right? N is less than 2, let's say 2 to the third, then true, else false. So let's go ahead and check that. We expect check to just tell us what the type is. And it does. We can do reduce. What do we expect 2 to be? Yep, it's true. What do we expect, say, 9 to be? That's, oh, whoops. That's false. I actually meant to do 9 before. False. 4. True. 0, also expect to be true. So that's just a very nice, simple way to do true-false statements. Very nice. You can just go ahead and use the lambda function with that natural input of n, and we can pull out things that you may need. So let's go ahead and look at the positive that we looked at here. We could say new definition, positive. I don't remember if we used that one before. Nat to a boolean. So we are going to have our lambda function for an input in as a natural number. Again, there are a lot of ways you can do this. It's totally up to you. I'm doing a bunch of different ones so that you can choose the one you like the most. And is greater than 0, then true, else false. And that's going to be a boolean. Whoops, actually let's keep the parentheses, because it's basically just input, output, so kind of need the parentheses for this one. Input is in a natural number, output is possibly true, possibly false, that's a boolean. All right, cool. And what if we want to just do this in other ways? I'm gonna actually move this to one line. What if we want to take off all this nat stuff? We could. Could we take off the boolean stuff? We could also do that, because it knows. It can infer it. Right? You could also do just, again, lambda n is greater than 0. Lee knows how to invalidate n is greater than 0. That is also a thing you could do. Sort of forgiving in this way. Other times, it can just be a bit of a pain. The syntax does get a bit time to get used to. That's why I always have a lot of problems with this. Again, you don't even need the natural to boolean type. You can have a definition positive. And we could bind, use a lambda n if n is greater than 0, then true, else, false. And you could also do that. So again, a lot of ways you can do it. It's up to you on what you want to do. And we can prove that all of these are the same. If we want to just throw down a theorem, oh my. Say positive is positive. Positive equals positive. Oof, we just did double prime this past time. We can actually just prove that with reflexive. So, no biggie there. No problems there. It's all the same thing. So, let's try a new one. We could actually put in multiple different things. We could have, it's called power. It's going to take in an x value, which is the natural number, a y value, which is also a natural number, bind directly, and it's going to be x to the y. And so when we're going to do evaluate for these, because I think Lean just used some sort of weird recursion to do reduce. So we're going to do power. What do we want x to be? Let's call x3. Let's make y6. We get 729, which we could easily do on a calculator and find the same thing. We could do very large numbers like 2 to the 16, 32, etc. But if we do reduce, Lean is going to chug that hard. So right now it's saying parsing it line 48. In a few moments it'll be like, it'll give us an error, just that I think we have a stack problem. Yep, deep recursion, increase stack space. So can't quite do that, gotta use evaluate, just keep that in mind depending on what sorts of items you're dealing with. So we notice that each one of these functions, they're basically functions, right? Has a type, right? We can't escape from that. Pretty much everything in Lean has a type. We explained that in day 1. And we can use these types to pass functions to other functions. All right? So we're gonna start embedding functions. I wanna test this real quick. If we can just say x, y. Okay, yeah, that works. Yeah, so that's another way you could do that one. It's basically like the proposition before. You have like P, Q, and that's propositions. Same idea. I just didn't want you guys to make like, do I have to use X nat and then Y nat? No, you can just put it all together. No big deal. So let's have a larger function. So we're going to call it compose. We have a function f. I'm going to do f, g, h, etc. because that's how math likes to do it. You'll have like f of x, and you'll have like a g of x, and then like, I think it's probably algebra where they talk about f of x, f of g of x, f of x, g of f of x, g of g of, so you get the idea. It's gonna be about the same idea in Lean. Actually, I'm gonna do nat to nat. So f is gonna be our natural number to a natural number, and we're gonna define g as also going to be a natural number to a natural number. We're going to have an input, x, which is a natural number. This is all, and our type is going to be a natural number. And right now it doesn't like us, so we're going to have the functions be f, g, x. So this is essentially just f of g of x. So this is going to g and x is going to evaluate first, and then that evaluation is going to come into f, and it's going to do that next. So let's go ahead and check compose so we can just look at all the types. So, okay, so see what we've got here. We have our natural to natural, our second natural to natural, and then our third one, natural, and that actually should give us a natural. Not totally on board with what Lena's complaining about. I think I just did an uppercase N. That's embarrassing. There we go. So we have a natural to a natural for a natural natural. It's okay. So this first set is our F. The second set is our G. The third one is our X. And the last one is our basically our return type. So what if we did a check of compose, and we're going to use previous functions. We have square and double. Let's go ahead and check what that works. Remember, square is a natural to natural, which matches F's type perfectly. Double is also a natural to natural, which matches G's type. And we check that, and we have compose, square, double, and all that's going to be for a natural, and it's going to give us natural. So what about we give it a number 3? What do we expect for this to give us? Right. It's just all it's done is replace that third natural, which we didn't know yet, with 3. So what if we actually wanted to actually know what this is? I'm going to use evaluate. We're going to do compose, square, double 3. And that's 36. Double of 3 is just 6. Square of 6 is just 36. If you wanted to, you could put these parentheses here, but compose is like, wait a moment, you were supposed to give me a natural, and then a single natural. So Lean does not like this. Because remember, it's type checking. Right? As soon as compose doesn't meet these qualifications, it's going to cut out. So remember, compose needs 2 functions, natural to natural, and a natural. What this is doing is you're satisfying that F, but this is turned into turned into 6. So suddenly it's like, wait, where's the G? You might have given me an A X over here, but I need a G. So if you threw a double here, that would work. But you can't put parentheses here. So there we get 144. Double of 3 is 6. Double of 6 is 12. Square of 12 is 144. So just keep that in mind. If we wanted something else, we could do such as a do twice. We need a new function. It's going to be a natural to natural. We have an X as an input. That's a natural number. Our type is going to be a natural number. And here's what we're going to make the function. So we're going to make it do a function f of x and that same function over that. Let's go ahead and check do twice. And we can see that It's a natural. It's taking in that natural, and it's going to give us a natural number. Perfect. So that was great, but how can we do that in lambda functions, right? So let's go ahead and do that. Let's have a definition. Do twice prime. We're going to write out basically the entire type. It's going to be a natural to a natural. Natural to natural. Whoops, I actually meant to R, natural. All right. So we're gonna have a function. That one input argument, however you want to call it. I guess technically this is just, could be also considered an argument, right? It's just a function. And this is what we're going to get out of it. So what about we just go ahead and bind that to something? We're going to have our lambda. Our function is going to be a natural to a natural. We're going to have an x, which is a natural number. And it's going to be f of x. Remember, this is what we're taking in. The syntax for this is just a comma, so we can split these up. So inputs, output. Perfect. Now we could even go more insane if we really wanted to. Let's do a definition of do twice. That's going to be pretty much the same thing. I'm going to copy this. And so we could have a lambda function of where f is natural to natural. All right. We're actually going to space that with a comma. And we're going to put another lambda function. This time it's taking an x, which is a natural. And for this, we're going to do f of x. So what do we do here? This lambda function is practically just embedded in this one. It's kind of weird, but intuitively you can figure this through. We have our function defined up here. And then this is essentially just another item. This is just a shorthand for this. All right? Nothing too crazy. So if we wanted to do just a definition of, I'm going to call it twice dub. Bind it directly to with do twice. And double. All right. What do we expect out of this when we evaluate it? Let's try 3. And we get 12. So 3 times 2 is 6. 6 times 2 is 12. Perfect. That is exactly what we want. Okay, wow, this one's taking a bit longer than I expected. But we're gonna finish it up, I think. All right. So here's what we've done so far. We've done explicit return types, we've done if else, and now we're throwing in all these functions here, right? So let's make a new one. We could have some other more or less simple-ish things. How about we make a definition sub do twice. We're going to give it a function, natural to natural, and we're going to bind it. We're going to have a lambda function. X is our input. That's going to be a natural. F, F, X. This is another sort of other way you could do it. Let's just go ahead and check that. And as we can see, it's pretty much the same thing. There's a lot of ways we can do this. It honestly starts to get pretty crazy. So, I mean, do what you think you need to do. Just because I don't want to throw you guys off with just insane things, you know? That would make me feel really badly. Yeah. Oof. So how can we just check to make sure that do twice actually does the same thing as do twice double prime? We could just do a definition of, let's say do twice equals do twice, and we'll have do twice equals do twice. How do we check to see if something is directly equal to something else? We can just use the reflexive property and it checks out, which is perfect. Lean is essentially just checking the types and then various types of types, and it loves us, so it's going to give us exactly what we want. Now what if we wanted to just put in all sorts of crazy things? Like what if we want to like take in even larger items, right? So let's make a new do twice definition. Do twice. This is gonna be our third one. Actually, I think it's like, yeah, actually this is our fourth one technically, right? We're gonna have a function of a natural number to a natural number to a natural number. I guess it's technically not two, it's just, you know, implies, a lot of implies. We're gonna have our x, and this time that's going to be a natural implies natural. Type natural natural. Oof, wow, I'm using a lot of space. Let's move this over slightly. Yeah, there we go. Bind f of x. Wow. So that was quite a bit, wasn't it? Yeah. So nothing much has changed. Just things have gotten a lot crazier now that we've really started to get into it, huh? So let's go ahead and check this. Just see all the types. And here's what we've got. Wow. That is a lot of implies. But it's nothing we can't handle, right? Right? Nothing much has changed. We still have that these are basically just arguments, and they're going to take in something with that type. Right? Nothing too big. So what if we just go ahead and check? If we do a do twice triple prime with a do twice, just the first one. All right? So we know that do twice satisfies that first condition because do twice is of that same exact type, right? If it didn't have that type, we run into the problem like before where Lean starts complaining. It was up here, the compose. When you didn't give Lean those correct arguments or types, it starts complaining. You don't need to do twice. You could have anything else, but it needs to be of that type, which is in implies in, implies in, implies in. That's what you need. And nothing else will satisfy that. All right, cool. So what if we actually just wanted to try to see what reduce looks like? Let's see this right here. And that is what we get. So not too bad. Basically looking at our function right here, actually does give us a lambda, which I think is interesting. So there we have it. So our function f is that, x is the second part, and we're using f on x for f of x. And you can mess with this however you please. Depends on what kind of functions you want to make. But that's pretty much it for functions. And I guess lambda functions, if-else statements, etc. I hope you found something interesting. I did this in a lot of different ways. Sometimes I put nat only, sometimes use the uppercase N. I guess just the natural symbol, because Z or Z for integers. But there's a lot of different ways you could do this exact same thing. It's completely up to you how you want to do it. But do what you think you'll be able to read in the future, right? Less isn't necessarily better, neither is more. You need to find out what works for you. I hope you found something interesting. I hope you found it helpful. I'm not a great teacher at this. I'm not a professional at Lean at all, so take everything with a grain of salt. But I hope you found it good. So take care. See you next time. I might do negation next time, because I think we looked at this one over here. So I want to get back over here soon. So take care, everybody. Hope you have a nice day. Goodbye.